Newton's ring. What you see in the diagram is experimental setup of Newton's ring. In this is the plano-convex lens L. In this setup, L is plano-convex lens, which is placed on the glass plate P. This is the glass plate P, which is placed on plain glass plate P. This G is another glass plate. It is a glass plate at kept at 45-degree angle with respect to the source. This is the source of light. So here S is monochromatic source of light. Say wavelength lambda. And here is the microscope. That M is microscope. So what happens in this case? Wavelength monochromatic source of light. From this we get the light rays, monochromatic rays. These rays fall on the glass plate first at G, where they are partially transmitted and partially reflected. Partially reflected light fall on this film. As you can see in this case, there is a thin air film formed between lens L and plate P. Here in this diagram, a thin air film is formed between lens L and glass plate P. And this light, which is reflected from the glass plate G, fall normally on this film, on the air film. It fall normally on the air film. And then the fringes are observed in microscope. These fringes are observed in microscope. What you see there is alternate dark and bright rings observed, which is concentric around the point of contact. In the microscope, you will see the rings. You will see alternate dark and bright rings like this. And there would be a center point over here. And around that center point, there would be dark and bright rings. So at point of contact, you will see the dark spot, and around that you will see alternate dark and bright rings. So at this point of contact over here, you will see the dark point, and around that dark point, you will see alternate dark and bright rings, which are called Newton's rings. Now, what would be, how come you see the Newton's ring, which are circular? For that, let's see, this is the glass plate L, lens L, and the glass plate P. And in between, there is a air film formed. Now, the light, say, monochromatic light is incident on this lens first, and initially it is reflected from the top surface of the air film as ray 1, and it is partly transmitted at this point. So at this point, let us say this is point A. At point A, incident ray is partly reflected and partly transmitted. This partly transmitted ray again reflected from the glass plate P as ray 2. So you can say that here ray 1 is reflected from top surface of air film, and ray 2 is reflected from bottom surface of air film, and in between there is a film thickness T. Then ray 1 and ray 2 are interfering and produce the interference pattern. As you can see, the film which is formed between the lens L and plate P is wedge-shaped film. Let us say that wedge is having an wedge angle alpha. So we already know that what would be the path difference between ray 1 and ray 2. We have derived that equation in the wedge-shaped air film, and the path difference is 2 mu t cos of r plus alpha plus lambda by 2, as the film is air film in this case. So we have added plus lambda by 2, as second ray is reflected from the glass plate, which is the denser medium. So this is the path difference between ray 1 and ray 2. Now as you can see in this experimental setup, these monochromatic rays are falling normally on the film. They are falling normally on the film. So let's see the condition for normal incidence. For normal incidence, angle of refraction is 0. For air film, mu is equals to 1. And this alpha is extremely small and can be neglected. Then part difference, this part difference would be delta equals to, now this mu is 1, so it is 2t. R is 0, alpha is neglected, so cos r plus alpha is equals to 1 plus lambda by 2. So this is the path difference between the ray 1 and ray 2, and the path difference is 2t plus lambda by 2. So as you can see here, variable is thickness T. So as the thickness changes, as you can see here, in this direction, the thickness will increase. So as the thickness changes, path difference changes, and accordingly you will get dark and bright rings. So here at the point of contact over here, thickness is 0. At point of contact, T is equals to 0, and therefore path difference is lambda by 2. And when path difference is lambda by 2 is the condition for destructive interference. That is, you will get the dark point at the center. At the point of contact, you will get the dark point. Then, when this 2t plus lambda by 2 is equals to n lambda, when 2t plus lambda by 2 is equals to n lambda, this is condition for constructive interference. So let us simplify this. Let's transfer this lambda by 2 to the RHS side. Then you get 2t is equals to 2n minus 1 lambda by 2, and this is condition for bright ring or a constructive interference. And when this 2t plus lambda by 2 is equals to 2n plus 1 lambda by 2, you will get destructive interference. That is, after simplification, when this 2t is equals to n lambda, you get dark ring. So these are the condition for bright ring and the dark ring. Now the question arises why we get dark ring. As you can see here, as I said, we get bright ring and the dark ring. But why we get bright and dark ring? As you can see here in this case, the path difference is introduced by varying thickness. As the thickness changes, path difference changes. So the path difference in this case depends on the thickness only, because thickness is the variable. And as you know that this L is the plano-convex lens, which is a circular, and hence locus of points having same thickness have same path difference. And which is possible in this case, that is possible along the circle. And therefore fringes are circular. So in this case, as you can see here, this is a plano-convex lens, which is a circular, which is kept on the glass plate. If this is the thickness over here T, and if that T satisfies, say, the condition for the dark, then this T, the thickness T, is same in locus of points around the circle. Around the circle, the thickness would remain same. So around the circle, that locus of points will have the same thickness. And if that thickness satisfies the condition for dark, let's say T satisfies condition for dark, then we get dark ring. And if that thickness T, at T we get dark ring. We are assuming that. Then as the thickness changes by lambda by 2, then we will get bright ring. And further, if the thickness is changes again by lambda by 2, then we will get dark ring. So as the thickness changes, we get alternate dark and bright rings. And the reason for getting the dark or bright ring is because locus of points having the same thickness have same part difference. And that is possible only in circle, as your lens is circular. Then let us find the relation between thickness and wavelength. Relation between thickness and wavelength. For that, let us consider this circle. This is the circle, and this circle, let us say that in this, there is a plain glass plate over here. At this point, there is a plain glass plate which is touching the circle, and in this circle, what is the lens actually? This lens would be the part of this circle. This is my lens over here. This is L point, this is over here, and this is L prime. So in this diagram, this LOL prime is lens, which is part of the circle. Okay, that lens LOL dash is lens, and that lens is a part of circle whose diameter is D. So this is the diameter of that circle, and radius whose center is, let's say, at point C over here. This is the center of that circle, and this is the radius of that circle R. So LOL dash is the length which is a part of circle with center C. Then this R is radius of that circle, but actually this R is radius of curvature of the lens also. This is radius of curvature of lens. This R is radius of curvature of lens R. Then at certain point, let us say in this case, at certain point, the thickness of the film is T. At this point, thickness is T. Similarly, At this point also, the thickness of the film is T, where I am getting a ring. What I am assuming is at this thickness T, I am getting the ring of radius R. So this distance and this distance over here up to the thickness T from the center is radius of ring. This is also radius of the ring. Let me name these points as Q here, N here, and P over here. This point is P. Okay. Then for bright ring, we know that for bright ring, what is the condition? For bright ring, this 2t is equals to, just now we derived this, 2t is equals to 2n minus 1 lambda by 2. This is the equation for the bright ring. Then from this diagram, which I have drawn now, we can write as per the properties of circle. I can write here this Qn into Np is equals to, let's say this point is D over here, is equals to dn into no. This is the property of the circle. The Qn into Np is equals to dn into no. So this Qn is R. As we know that this is R. Np is also equals to R. This dn, that dn is actually 2R minus t, because this thickness from this point to this point is t. So dn is 2R minus t into no. No is t. So we can write this as R square is equals to 2RT minus t square. T is the thickness and thickness is small. Thickness is small and hence t square will be very small and can be neglected. So we are going to neglect t square as t is a small. T square would be very small. So let us neglect t square, and what we get is r square is equals to 2rt, or t is equals to r square upon 2r. Now I got here the value of the thickness. I know for bright ring 2t is equals to 2n minus 1 lambda by 2. So here let us consider for bright ring. For bright ring, this 2t is equals to odd multiple of lambda by 2. So let us replace this t with r square upon 2r. 2 into r square upon 2r is odd multiple of lambda by 2. In this case, n start with 1, 2, etc. So this 2 cancels with this 2, and what we get is r square is equals to 2n minus 1 lambda r upon 2. In this case, we are talking about the diameter of the ring. This r is radius of the ring. So let us convert this into diameter of the ring. So we get d square, which is the diameter of the ring, divided by 4 is equals to 2n minus 1 lambda r upon 2, since R is equals to diameter half, d by 2. So we get d square is equals to 2 into 2n minus 1 lambda r. So this d is the diameter of first ring, second ring of any ring. So I will write, instead of just writing diameter square, I will write d suffix n. N is the ring number, which would equals to square root of 2 2n minus 1 lambda r. Or I can write this as diameter of bright ring is directly proportional to square root of 2n minus 1. So diameter of the bright ring is, let's write this, diameter of bright rings is directly proportional to square root of odd natural number. This 2n minus 1 is odd number, odd natural number. So we can write that diameter of the bright ring is directly proportional to square root of odd natural numbers. That's what we have proved here. Then consider dark ring. For dark ring, we know that this 2t is equals to n lambda. Let us replace this t with this, this quantity r square upon 2r. So 2 into r square upon 2r is equals to n lambda, or r square is equals to n lambda r, or d square is equals to 4n lambda r, since r is equals to d by 2, diameter half. Or I can write diameter of nth ring is equals to 2 into square bracket n lambda r, or diameter of nth ring is directly proportional to square root of n, because this lambda r and 2 are constant. Only variable is n, and n is natural number. Therefore, we can write here that diameter of dark rings are proportional to square root of natural numbers. So this is what we have proved, that diameter of dark ring is proportional to square root of natural number. So this is what we have studied for dark rings and bright rings, or these dark and bright rings are called Newton's rings, as Newton gave explanation to this phenomena. These Newton's rings are used for measurement of wavelength. This experiment, particularly used for determination of the wavelength. So let us see the first application. The first application is determination of wavelength. Now we have to perform the experiment. As you can see, the simplest example, simplest equation is for the dark ring. For the dark ring, diameter square is equals to 4n lambda. So we will consider the nth dark ring. Now in this case, the film between the lens and the glass plate is air. The film is air. And we have to find diameter of nth dark ring, and that is given by the equation diameter square of nth ring is equals to 4n lambda r. As you see in this equation, lambda is the wavelength, capital R is radius of curvature of lens, n is ring number. So this is the equation for diameter of nth dark ring. Let us say this is equation 1. So first find the diameter of some nth dark ring. Then find the diameter of n plus mth dark ring. And the equation for that would be diameter square of n plus mth ring is equals to 4 in bracket n plus m lambda r. And this is equation 2. Take the difference between equation 2 and equation 1. Equation 2 minus equation 1 will get diameter square of n plus m ring minus diameter square of n ring is equals to 4m lambda r. What we have to find is wavelength. So wavelength is equals to diameter square of n plus m ring minus diameter square of n ring divided by 4mr. So using this equation, you can find the wavelength of the given source. What we have to do is consider some waves, consider some rings. Maybe fourth ring is nth ring and 10th ring is n plus mth ring. Find the diameter of the two dark rings, use this equation and find the wavelength. Second application of the Newton's ring is you can find refractive index of the given liquid. So second application is determination of refractive index, refractive index of liquid. So using the Newton's ring experiment, you can find the refractive index of the given liquid. So initially, we have to perform the experiment. There are two parts. In the part 1, perform experiment using air film. And you know that for the air film, this mu is equals to 1. And find the diameter of nth ring and diameter of n plus mth ring. So d square of nth ring is equals to 4n lambda r. This is the diameter of nth dark ring. Then diameter square of n plus mth ring is equals to 4 into bracket n plus m into lambda r. And this is diameter of n plus mth dark ring. So this is equation 1. Let's say this is equation 2. Then equation 2 minus equation 1 will give you diameter square of n plus mth ring minus diameter square of nth ring is equals to 4m lambda r. And this is our equation 3. So this is the part 1 of the experiment. Then in the part 2, perform the experiment using the liquid. liquid film of refractive index, say mu, and we have to find this mu. So we have to replace the air film initially, as you see here in this diagram. Initially, there is a air film between the lengths L and P. Now we have to fill that space with the liquid. Now there is a liquid film. And then find the diameter of same ring number. Same rings. So let us find now the diameter of nth ring. Nth dark ring. As we are introducing the liquid, the diameter will change. So let us write d prime square of nth ring is equals to 4n lambda r. Now mu is not 1, so we have to divide it by mu. So this is the diameter square of nth dark ring when the film is liquid. Then for n plus mth dark ring, so d prime square of n plus mth dark ring is equals to 4n plus m into lambda r divided by mu. This is equation 4. This is 5. Let us take the difference. Equation 5 minus equation 4. This is a prime over here. That would be d prime square of n plus m ring minus d prime square of n ring, and that is equals to 4m lambda r divided by mu. And this is equation 6. Then what we'll do is equation 4, not equation 4. We have here equation 3 here. Equation 3. So equation 3 divided by equation 6. Equation 3 by equation 6. Equation 3 is LHS is this, and LHS of equation 6 is this. So what we get is diameter square of n plus m ring minus diameter square of n ring divided by d prime square of n plus m ring minus d prime square of n ring, and then this one RHS side 4m lambda r divided by 4m lambda r by mu, so that this 4m lambda r will cancel and you will get the mu. So using this equation you can find refractive index of the given liquid.